Hello again, everyone. Welcome to our discussion of section 6.1, where we will be talking about solving systems of two linear equations. So linear equations, as you know, produce a straight line. So when we solve a system of two linear equations, that means we're looking for wherever these two lines may intersect. Now, sometimes lines may intersect at a unique point. Sometimes they may not, in which case they would be parallel lines where they would never intersect each other. So such systems will have no solution. Or two lines might be completely overlapping at every point along their lengths, in which case we would say that the system has infinitely many solutions. Therefore, a system can have one unique solution, which would be one point of intersection, or no solution, which would be for two parallel lines, or it may have infinitely many solutions, in which case the lines overlap completely. Before we go into the details of that, let me remind you to please skim through, take about 30 minutes to 45 minutes to skim through this section 6.1 in your book. Attend the class or watch this video after that, and take careful notes about anything you see that you might think it's important, or anything that might be of a question to you. Then revisit the section in the book. This time solve all the problems you see that the book has already solved as examples. Resolve those examples without looking at the book solutions, and then come back to the video, watch these examples that I go over without looking at the solutions. So in other words, preferably, even when you watch these videos for the first time, you would want to pause the video, solve each problem on your own, and then unpause the video and compare your solution with these. And of course, complete all the homework assignments by the due date, and please review the previous material. That should not take you more than half an hour each week. So 30 minutes each week, please spend reviewing the previous material in order to keep everything fresh in your mind. So as we said, the systems of equations, linear equations in two variables, they may not intersect. In other words, they may or may not intersect. If they intersect, then the point of solution is called the solution of the system. Okay, wherever they intersect, that's the solution of the system. And as we said, there are three types of solutions. One, if there are if the system has at least one solution, that's when the two lines intersect at least one point, or infinitely many points. So if system has no solution, right, the two lines are parallel. And if a system has infinitely many solutions, the two lines overlap completely. And the names that you see me underlining there, that's just the names that your book uses. And I wanted to show those just in case you see those names elsewhere, you know what they refer to. So consistent systems are systems that have one unique solution. Inconsistent systems are systems that have no solution, and dependent systems are systems that have infinitely many solutions. And here are graphical examples of each of those cases. Okay, so you have, in this case, you have exactly one solution, right? Those two lines intersect at that point. And that intersection point is called the solution of the system. That point is the solution of the system. And consistent or dependent systems are systems that have infinitely many solutions. In other words, you do have two lines there, but because they overlap completely, you only see one line. But there are two lines there that are completely superimposed on each other along their full lengths. And finally, inconsistent systems are systems that have no solution, which means the two lines are parallel. So to solve systems of linear equations in two variables, there are two main methods that are used to solve a system of this type. And those are the substitution method and the elimination method. And these are, we're talking about two linear equations in two variables, where they have the substitution or elimination method. In section 6.2, we will be talking about systems of three equations in three variables. The method there is about 30% different than this method. So this method, I'm just reminding you or emphasizing that the method we're discussing here, the substitution and elimination method, only applies to systems of two equations, two unknowns. This method does not apply as you see it this way to systems of linear equations of three equations, three unknowns. In other words, when we solve systems of three equations and three unknowns, there is a 30% of the solution or procedure that we have to finish first before we can apply to this method or apply this method. What is that, the 30% then? That is not the same thing. Well, if you have three equations, three unknowns, you must reduce that equation, that system, to two equations, two unknowns. Only after you've done that, you can apply the method we're talking about now, or we will be talking about shortly. Okay? So once again, when we get to section 6.2, which is when we will be solving systems of three equations, three unknowns, that method is different than this because we need to reduce that system of three equations, three unknowns to a system of two equations, two unknowns before we can apply this method. Okay, so please remember that. All right, so how does the method of substitution work? The best way to demonstrate this is to just go ahead and show an example. The first thing you should make sure that is true is that both of these equations must be set up such that the variables are on the left and the constants are on the right. Now, the first equation fulfills that format, but the second equation does not. So I must move this negative 3y to the left. When I do that, then the equation will have the proper format. Okay, so let's do that. So the top equation is okay. The bottom equation, let's move minus 3y to the left. It becomes positive 3y, like that. Now notice that in both equations, both variables that we're solving for are on the left, and the constants are on the right. The other thing you should notice is that the order of variables is consistent with x, y, or if you had three variables, x, y, z, and so on. So we would not want to have y, 4y here and plus x here. The variables should be in order, and they should be on the same side, on the left. Okay? So now we are ready to solve, use the substitution method here. So the way the method of substitution works is that you solve for one of the variables using either equation. So let's say you solve for x. Then you substitute that in the other equation and you solve for the variable, one of the variables. Once you have the solution for one of the variables, then you look for the other variable. So let's do that. So I'm going to use the bottom equation to write x equals, again, minus 3y plus 3. Right? So I went back to that way. I started with the system with both variables on one side equal to the constant. Now I want to replace x in the top equation. So I solve for x. Now we have that. Now I'm going to substitute this whole thing for x in the top equation. So using x plus 4y equals 6, now put all of this because the x is equal to that. So replace x here with all of that. So minus 3y plus 3, x became all of that, plus 4y equals 6. Okay. Now we can simply combine minus 3y plus 4y. Right? Minus 3y plus 4y is positive y. Plus 3 equals 6. Now move the positive 3 to the other side. So we have 6 minus 3. And therefore y is equal to 3. So that's one of the variables that we solved for. Okay? That's one of the variables. Now we can replace for y with 3 in any of the original equations and solve for x. Okay? Let's do that with the bottom equation. We can still use that. So now using x equals, once again, x equals minus 3y plus 3, substitute for y with 3. So x equals minus 3 times 3 plus 3. And this is minus 9 plus 3. So x equals minus 6. Okay? So this is the x component. So what have we discovered? We've discovered that these two lines in the system intersect each other at one point. And the coordinates of that point are minus 6, 3. Okay? That's called the solution of the system. Okay? So this is the solution of the system. The two lines intersect each other at that point. All right? So then in this case, let us solve the next system here. But before we do that, I wanna show this on computer. I want to show these two lines on the computer so you can see that they intersect each other. Okay? As I transition from the dock camera to the computer, you're going to see a glitch on the screen. Please ignore that. Okay? We'll be back to the dock camera shortly. So now we have x plus 4y equals 6. There's the line. And the other line was x equals minus 3y plus 3. Notice that we can zoom in on that point. Notice that point of intersection where the red and blue line intersect. We figured out that that point is minus 6, 3. And look at the green dot. It snapped to it. Okay? So we found that point of intersection for those two lines. I just wanted to show you this before we go back to the dock camera. Okay. All right. So now we're back. Now this time, please pause the video, solve this system, and then come back to the video after you're done. All right, I'm assuming that you're done that. And so let me present my solution here. Again, we're going to apply the method of substitution. This time, I'm going to use the top equation to solve for x. X equals, I'm going to send minus 2y to the other side, so it'll be 2y plus 3, right? Minus 2y on the left, when I move it, it becomes positive 2y. Now, in the bottom equation, I'm going to replace for x with what I have, 2y plus 3. So, using 2x equals 4y plus 6, we have, this is x, right? X equals 2y plus 3. So I'm going to replace 2 times 2y plus 3 equals 4y plus 6. Okay? We're solving for y now after substitution. So 2 times 2y is 4y. 2 times 3, 6. On the other side, of course, we have 4y plus 6. So in this case, watch what happens. When we move all the both terms that have variable y in them to the left and the constants to the other side. So we end up with 4y minus 4y equals 6. Moving this 6 to over, we get that. So what do we get? We get 0 equals 0. Notice 2 things about this, what we ended up with. First of all, it is always true. 0 is always equal to 0, right? There is no invalid statement there. That's a valid statement. 0 equals 0. The second thing that should catch your attention, this equation 0 equals 0 does not depend on the value of either x or y. Because remember, in the above case, where there was a unique solution, which we saw graphically and we found a solution for, there was the value of the equation y in this equation, the result of this substitution dependent on the value of the variable y being equal to 3. And when we solve for x, again, we ended up with an equation where we had to solve for x, right? That's when we had one unique solution. But in this case, in case B, this result does not depend on either x or y. We were hoping that it would depend on y, but it doesn't. It just, y ended up canceling. Right? When this happens, that means we have infinitely many solutions. That means we do not have to solve for x, because we have infinitely many solutions, which means these two lines overlap completely along their lengths. Okay, so this means infinitely many solutions. Okay, this is otherwise known as a dependent system. Okay, that's the result. And 0 equals 0, again, that's a valid statement. 0 is always equal to 0. Okay, there's no argument there. So we've now seen an example with one unique solution. Then we saw an example with infinitely many solutions. And let's look at another example here. This might be parallel, but let's find out. I don't know. I really don't remember until I solve it. Okay, so once again, we're going to use the method of substitution, which means we're going to solve for one variable first. Let's say x. equals minus y plus 1, right? Minus y. So I just sent my y to the other side. Now we have minus y. Now let's substitute for x in the top equation. So using 5x plus 3y equals negative 1, let's substitute for x with that, because x equals minus y plus 1. All right? So 5 times, instead of x, let's plug in, substitute minus y plus 1 plus 3y equals negative 1. Now let's distribute minus 5y. 5 times minus y, minus 5y. Plus, 5 times 1, 5. Plus 3y equals negative 1. Let's combine the y terms. We get minus 2y equals 5. Let's move the positive 5 to the other side. It becomes minus 5. Minus 2y equals minus 6. Y equals minus 6, right? We're isolating y because we're solving for y. So we need to get rid of the negative 2. So divide both sides by negative 2. And negative divided by negative is positive. So we end up with y equals 3. So we found one of the solutions here. So the two lines are indeed not parallel. So then let's substitute for y with 3 in any of these equations. This seems to be the easiest one. So let's use that. Use whichever equation that is easier. Using x plus y equals 1. So I'm using the bottom equation. Then replace for y with 3. So we have x plus 3 equals 1. Let's move the positive 3 to the other side. When we do that, this becomes minus 3. And then, of course, x equals negative 2. Okay, so we found the x and y. So that system has a unique solution at negative 2, at point negative 2 comma 3, like that. Okay. Okay. The elimination method is very similar to method of substitution, but it requires us to eliminate one of the variables first. Okay, but so we eliminate one of the variables, solve for the other variable that remains, and then whatever we get for the remaining variable, we substitute back in one of the original equations to solve the other variable. Okay, so it's basically elimination then substitution. Okay, all right, so it's up to us which variable to eliminate first. Eliminate the one that is easier to eliminate. For example, I'm looking at these two equations and looks like we can easily eliminate the x terms because their coefficients are equal and opposite already. We don't need to do anything to these equations. Just add them and we are able to eliminate the x term. So let's do that. So just adding, we can do that, right? Because we notice that x terms have equal and opposite coefficients. So we know that if we add these two, the x terms drop out. So we end up with 4y minus 5y plus that, right? 4y plus minus 5y is minus y equals minus 2 plus 1 is minus 1. Therefore, y equals 1. All right? Like that. Y equals 1. So now, substitute this y equals 1 into any of the previous original equations to solve for x. So let's use whichever one is easier. I'll use the bottom one. So using minus 3x minus 5y equals 1. And then for y, we're going to substitute 1 for it. So minus 3x minus 5 times minus 1, sorry, no, not minus 1 equals 1. So minus 3x minus 5 equals 1, right? Minus 5 times 1 is minus 5. We're solving for x, so we need to isolate x. So we need to get rid of this negative 5. How? Move it to the other side. Negative 3x equals 1 plus 5. It was minus on this side. When we move it, it becomes positive 5. So minus 3x equals 6. Now, is x isolated? No. It's got a negative 3 next to it. How do we get rid of it? Divide both sides by negative 3. On the left, the negative 3's cancel out. We end up with x equals minus 2 on the right. Okay, so that's one of the solution for one of the variables. How about y? Well, we can substitute now for x in any of these equations and solve for y. Let's substitute in the top equation there. So using 3x plus 4y equals minus 2, right? Let's substitute for x with negative 2. 3 times negative 2 plus 4y equals minus 2. So we have minus 6 plus 4y equals minus 2. We're solving for y, so we need to isolate y. This negative 6 and 4 we need to get rid of. How do we get rid of negative 6? Send it to the other side. It's negative on this side. When you move it to the other side, it becomes positive 6. So 4y equals negative 2 plus 6. Then combine those two, we get positive 4. Now what? The y, is y isolated? No, it's got a 4 next to it, right? How do we get rid of it? We divide both sides by 4. We end up with y equals 1. So we've now solved for the value of y. Okay, so we have x coming from here and y from here. So the solution of the system is negative 2 comma 1. Okay, at that point, these two lines intersect. Let me move this down. These two lines intersect each other at that point. And you can plot this on a computer. If you go to desmoscalculator.com, just like the ones I've been showing you on the computer, you can actually see that point of intersection. Okay, so next, let's look at, we're going to continue using the method of elimination to solve these remaining systems. Okay. Again, please pause the video at this point and solve this system, and then unpause the video to see my solution. Okay, so I'm assuming you've done that and now you're back. The idea behind solving, once again, is isolating the variables, right? But look at this case. We have a parenthesis which groups the variables. As long as variables are part of a group, we cannot solve for them. Which means, to begin with, we have to distribute this 7 into this parenthesis in order to ungroup the variables that we're solving for in the top equation, right? So when we do that, we end up with 7x minus 7y equals 14. And the other equation is 2x equals y plus 5. The other thing you should know, so we've now ungrouped the variables x and y in the top equation, but are we still, do we still have the right format for this system? What do you think? No, we don't, right? We do not have, the bottom equation is not in the right format. To put the bottom equation in the right format, we must make sure that both variables are on the same side, are on the left, and the only term on the right is the constant 5. So let's do that. Let's move y to the left. Right? Y was positive on the right. When I moved it to the left, it became negative. All right, so now this system has equations that are in proper format for a system. Now, let's eliminate one of these variables. We can either choose to eliminate the x variables or the y variables. Whichever variable we choose to eliminate, we must make sure that that variable has equal coefficients that are equal but opposite in sign, in algebraic sign. So I think y, in this case, y is an easier variable to eliminate. It would be hard, it would be more work to get the x terms or the x variables to have equal but opposite coefficients. But it's easier to do it for y. How's that? Well, compare the coefficients. All we have to do to make sure that this y term has equal but opposite coefficient compared to that, to negative 7, all we have to do is multiply the bottom equation by something. What should I multiply the bottom equation by to make sure that the y term has equal but opposite coefficient when compared to the top equation? What should I multiply the bottom equation by? Do you see what term that is? Minus 7, right? Minus 7 times minus y will produce positive 7y, which is equal, which means the y term here will have equal but opposite coefficient compared to that, which means then we can add them and cancel the y terms. So let's do it. And the top equation is still the same. So minus 7 times 2x is minus 14x. Minus 7 times minus y plus 7y equals minus 7 times 5 minus 35. Now add the two equations. All right, as we expected, the y terms add up to 0, right? Minus 7y plus 7y is 0. Now, add the x terms. 7x minus 14x adds up to minus 7x. On the right, minus 35 plus 14, it's going to be minus 21. Right? So, let's solve for x. X is not isolated. It's got a negative 7 next to it. So divide both sides by negative 7. Divide both sides by negative 7. On the left, we end up with just x. On the right, negative divided by negative is positive. 21 divided by 7, positive 3. So that's the value for x. Now for y, we can substitute for x in either of these two equations and solve for y. Let's substitute in the bottom equation, right? So let's do this. Using 2x equals y plus 5, then we have substitute for x with 3. So 2 times 3 equals y plus 5. And so we have 6 equals y plus 5. And of course, all we have to do is to solve for y is move the positive 5 to the left. It becomes negative 5, right? So we have 6 minus 5 equals y. And so y equals 6 minus 5 is 1. So there we have that solution for y. When we combine these two, then that system, those two lines intersect each other at this point, 3, 1. Okay. All right. So that's what is called the solution of the system. If you plug that point in that in either equation, the equation is valid. So 2 times 3 is 6 equals 1 plus 5 is 6. 7 times x minus y would be 3 minus 1, which is 2. 2 times 7 is 14, which is equal to 14 on the right. So you can test your solution always that way. Okay, in this case, once again, please pause the video, solve this system on your own, and then come back to the video after you're done. Okay? All right, I'm assuming you've done that, and now you're back. So, we can eliminate either x or y, but in this case, it looks like that the x terms are much easier to, well, actually, the y terms are just as easy to eliminate. So let's see. Okay, let's eliminate the y terms this time. The coefficients are okay because 0.4 is a multiple of 0.2 and 0.6 is a multiple of minus 0.3, right? So we can multiply the top equation by a term to make the coefficients of the y term equal and opposite to each other. What number, what value should I multiply the top equation by to get a coefficient for y that is equal and opposite to 0.6? Well, just 2, right? Multiply the top equation by 2. Because 2 times 0.3 is 0.6. We can quickly test that. So we have 2 times 0.3, 0.6, right? Okay, so now let's distribute the 2 into this whole equation. 2 times 0.2x is 0.4x. Minus. 2 times 0.3y is 0.6y equals 2 times 0.3, 0.6. The bottom equation stays the same. Like that. So let's add the two equations together. Minus 0.6y and positive 0.6y add up to 0. Then we end up with 0.4 plus 0.4x. It's 0.8x equals, on the right, 0.6 minus 0.2 is 0.4. So we're solving for x. We need to isolate x. Is x isolated? No, it's got a 0.8 next to it. So let's divide both sides by 0.8. On the left, we have x, because these cancel each other out. And we have 0.4 divided by 0.8. That's 1/2, right? Or 0.5. Let's see. Just to make sure. With these decimal numbers, you never know. Like that. So 0.5. So 0.5. So that's the value of x. Now let's use this to So this is the method of elimination, basically. By multiplying one of the equations by a number, we get rid of one of the variables, and then we solve for the other variable, and then we substitute back with this known value to solve for the other variable, which is, in this case, it's the y variable we're going to solve for. So we can substitute this back to either of the original equations. Let's substitute in the top equation. It looks to be an easier equation to work with. So using 0.2x minus 0.3y equals 0.3, we're going to plug in that. So 0.2 times 0.5, right? For x, we substitute for with 0.5, minus 0.3y equals 0.3. So what is that? 0.25 times 0.5, is that 0.01? Let's find out. 0.2 times 0.5, 0.1. Okay, so this is 0.1 minus, right? So this is 0.1 minus 0.3y equals 0.3. Okay. Okay, so let's keep the variable term on one side and keep all the constants on one side. I'm going to move this positive 0.1 to the right-hand side. When I do, this becomes negative 0.1. So minus 0.3y equals 0.3 minus 0.1. Okay, so we end up with minus 0.3y equals 0.2, right? Now we're going to solve for y, so we need to, oops, the screen looks a little bit fuzzy or out of focus. Okay, it looks better now. All right, so we need to divide both sides by minus 0.3 to isolate y, right? Oops. So from this, y equals, let's find out what is 0.2 divided by minus 0.3. 0.2 divided by minus 0.3. Negative 0.6667. So we end up with minus 0.6667. Okay, like that. So basically, we can keep these in decimal forms or in fraction form. The fraction form is more desirable because it is more exact. So we can write the solution this way. Let me, using these two, let's write the solution in this way. Either we can say 0.5 comma minus 0.6667, either that, or we can say 1/2 comma minus 2/3. Either that, either you can leave this is more exact, so this is preferable, okay, because that one was rounded. But I show both solutions just in case. Okay. Okay, so everything we've done so far has applications in business and science. So in the next few examples, we're going to look at these applications. Okay. So for example, in business, supply has its own equation and demand has its own equation, two linear equations, and we're talking about linear equations, right? Because supply and demand equations can be nonlinear. They can be any equation, but because our discussion here is about solving systems of linear equations, we're talking about supply and demand equations that are linear. So when we're talking about a business application of what we've been doing, which is solving systems of linear equations in two unknowns, then if the equations are called supply and demand, if the equations represent supply and demand, then that point where they intersect, where they have a solution, it's called the equilibrium point. Okay? So once again, if a system that is consistent of linear equations for supply and demand, once you solve the system, if and when it has one unique solution, that unique solution is called the equilibrium point, because at that point there is an equilibrium between supply and demand. There is an equality or equilibrium between what the customers want to demand or purchase in the marketplace and what the suppliers are willing to supply to the market at a specific price. Okay? So equilibrium point is that. So the price at which the amount of the product that the seller is willing to supply is the same as the amount demanded by the consumer is called the equilibrium price. So the price at which, if you're manufacturing something and the customers, and you want to sell that piece of manufactured product for $10 a piece, and if the customers are willing to pay $10 for that piece, then that is called the equilibrium price, because you as the producer want to sell that piece for a price that the customers would like to pay for that piece. So that's the equilibrium price. And when there's a very useful point or point of calculation in business, it's called the break-even point. That's when revenue and cost are equal. That's where supply and demand are equal. So break-even point is where revenue equals cost. All right. So in the United States, here are examples. Please pause the video, read this word problem. Remember what we talked about solving word problems earlier, in the earlier videos or lessons. We said that the first thing you need to do is find out what is not known and assign a variable to it. So do that. Make sure that when you solve this on your own, that you assign variables to the unknown. So here it says, I'm assuming you've done that and now you have your own solution ready. So in 2013, the United States has spent $452 billion more. The key word is more, not 452 billion, but 450 billion more on the military than China spent on its military. Together, China and the United States spent 828 billion. Find the amount spent on the military in China and United States. So let's assign variables to these things that we want to find, they want us to find out. The amount spent on the military in China and the United States. So I'm going to use U for the amount spent on military in the United States. Okay, and let's say capital letter C for the amount spent on military in China. Okay. Now what do we know? Once we have introduced these variables, let's translate the rest of the information. We know that in the United States has spent this much more on the military than China. So U, the amount spent on military in the United States, is equal to 452 billion plus C, which is the amount that China has spent. So that gives us one equation. Okay, we have two variables that for which we're solving because they asked us to do that. So that means we're going to need two equations. Two variables, we're going to need two equations. Three variables, we're going to need three equations, and so on. Then it says, together, China and the United States has spent $828 billion. So United States, or China plus United States, that's together, China plus United States has spent $828 billion on military. Okay, so now we have two equations, two unknowns. Does this look familiar or what? It does look familiar, right? That's a system of two equations, linear equations in two unknowns. So the rule says, if you remember, that the variables must be on one side, the constant on the other. So that we need to organize that equation. But we don't have to, right? We can just use the method of substitution. We can do that too. I'm thinking more in terms of section 6.2, and I shouldn't because we're in section 6.1, because in section 6.2 we must have these variables in order on the left. Otherwise the solution will not take off. It will not work. In the beginning, we must have all the variables aligned on the left. But in this case, we can get away with it because this is a system of two equations. So we can use the method of substitution. We already have an equation for u. We can substitute in the second equation with this, solve for c, the amount spent on military in China, and then substitute it back into this equation and figure out the amount for United States. Let's do that. So I'm going to substitute for u with this, 452 plus c. So c plus 452 plus c, right? Instead of u, I substituted all of that, equals 828. So what do we have? We have 2c on the left. On the right, we have 828 minus 452. So 2c equals, let's see. So we have 828 minus 452. 376, right? That's 376. But to solve for c, we need to divide both sides by 2, right? Let's do that. Let's do that here. So we have c equals 376 divided by 2, which means the amount of money spent on military in China was 376 divided by 2. $188 billion. That's the amount spent on military in China in 2013. So what was it for United States then? Well, for United States, we have this equation, right? United States, as we were told, spent $452 billion more. So let's figure that out. U equals 452 plus 188. So the amount spent on defense, on military in the United States is 188 plus 452, 640 billion. Okay. And of course, those two, if you add up those two, you will end up with $828 billion. Okay, that's the idea. Okay, I hope this matches the result, the solution you had when you solved this on your own, this problem. Okay, so then the next problem, once again, please pause the video. There it is in front of you. Solve this problem on your own before you see my solution. Okay, all right. So I'm assuming you've done that and now you're back. So one evening, 1,500 concert tickets were sold for the Fairmont Summer Jazz Festival. Tickets cost $25 for a covered pavilion seat and $15 for a lawn seat. Total receipts were $28,500. How many of each type of tickets were sold? Okay, so they're asking how many of each type of ticket. So we need to introduce variables for each type of ticket because they're asking for how many of each, right? So let's say that for a covered pavilion, so let's say C is number of tickets for a covered pavilion seat. Okay, so let's assume that variable represents that. Then let's say that for the other kind of seat, for the lawn seat, L represents that number of tickets for a lawn seat. Okay. I don't know, the screen looks a little bit out of focus. Okay, it now got, it's refocusing itself, but okay, it's better now. Okay, so now we know that the total tickets that of each kind that were sold, the total of those, one evening 1,500 concert tickets were sold. So C plus L, the total tickets were 1,500 tickets were sold of both kinds, right? Covered pavilion seats plus lawn seats, 1,500 such tickets were sold, the total for everything, both kinds of seats. Then we are told that the pavilion seats, that one, covered pavilion seats cost $25. So these tickets were sold or cost the customer $25 a piece, and the lawn seats cost the customers $15 a piece. Of course, right? The covered pavilion seats are more expensive because you are shielded from the sun and the other elements of the environment that the lawn seats are not protected against. Okay, so then we know that collectively the total receipts were $28,500. Okay, so then that would mean that $25 a piece times number of tickets of the covered pavilion seats, $25 a piece, times that, plus 15 times L, or $15 a piece for each lawn seat, must equal, the total of this must equal $28,500. Okay? So right there, we have a system of two linear equations, and we know exactly how to solve these. So the initial part, remember, all word problems are the same. You should read the problem first, once, if not if not enough, maybe twice or 3 times or even more. It doesn't matter. It's okay to do that. To then get a feel for what the problem is asking for and what is not known, what is known, and how to best establish a relationship between the knowns and the unknown quantities. And we've done that here. But the beginning point before all of this is you must introduce your own variables. We did that here. Some of you might choose to do X and Y. I chose to do C and L because I can better keep track of which variable represents which item in the problem. Okay? But you must introduce the variables first and then attach information to those variables and then translate using these variables and this information, translate what's given to you in plain English into the symbolic mathematical form. Now that's the system, and we know how to solve these systems. So let's say that I want to eliminate the L variable and then solve for C and then come back and solve for L. But let's eliminate the variable L. To do that, I have a plus 15 coefficient for this L, so I want minus 15L coefficient for that in the top equation. So I'm going to multiply the top equation by minus 15. Okay, so what do we have then? We have minus 15C, right? We're distributing this to everything. Minus 15L equals minus 15 times 1500 minus, let's figure out what is that quantity. Minus 15 times 1500 times 1500, we get minus 22,500. Okay, minus 22,500. The bottom equation stays the same. Notice that now the L terms have coefficients that are equal but have opposite algebraic signs, which is exactly what we wanted to have before we can add these two equations. So adding these two gives us 0, which we intended. Minus 15C plus 25C, that's positive 10C, equals, adding up these two, what do we get? 28,500. 28,500 minus 22,500, we get 6,000. Right? 6,000. So now we're solving for C, which means we need to isolate C. Is C isolated? No, it's got a 10 next to it. We need to get rid of that 10. How? Divide both sides by 10. Okay? So we end up with C being 600. So 600 covered pavilion seats were sold that night. What about the lawn seats? How many of those? Well, that's easy to determine because we knew that total number of tickets sold were 1,500. Right? So let's plug into that equation for C with 600 and solve for L. We already know L must have been 900 tickets, right? But this is how we can arrive at that. So using C plus L equals 500, we have 600 plus L equals 1,500. L equals 1,500 minus 600. L is equal to 900. So we have 900 lawn seats and 600 covered lawn seats that were sold that night. I hope this matches your own solution. So this is the trend for solving all these word problems. As I'm saying this, I'm looking at the next problem that is coming up. So usually, yes, you can introduce the variables and establish a relationship between them and solve the problem. Sometimes, though, looking at the next problem that is coming up, drawing a picture would also help. Usually, with some of the physical type or scientific type of problems, usually a picture would help. Okay, such as this problem. So this one says that it says, so you can go ahead, read this problem and solve it on your own. Spend no more than 20 minutes on this, but that 15-20 minutes, please give it your best shot. Think about it, solve it as if this was you were taking an exam, a final exam with one problem on it. This was the only problem. I mean, with that much focus and attention, try to solve this in 15-20 minutes. Okay? With that much seriousness and tenacity, try to solve this on your own without looking at anyone else's solutions. Then come back to the video. All right, so I'm assuming you've done that, and now you're back. This says a DC-10 airplane travels 3,000 kilometers with a tailwind in 3 hours. It travels the same distance, 3,000 kilometers, with a headwind in 4 hours. Okay? So tailwind it means the wind and the plane are moving in the same direction. Okay, that's tailwind. The headwind means the wind and plane are moving in the opposite direction. Opposite directions. Okay? That's what that means. So, then let's set up an equation for each case. For the plane and the wind going in the same direction, for this plane to travel 3,000 kilometers, and then another equation for the headwind, keeping in mind that it's taking the plane less time to travel the same distance with a tailwind than it does for the plane to travel the same distance with a headwind. It takes the plane 3 hours to travel the 3,000 kilometers with a tailwind, and it takes the plane 4 hours to travel the same distance with a headwind. Okay? So, distance, but the distance doesn't change, right? The distance is 3,000 kilometers. So, time, and they're asking for find the speed of the plane and the speed of the wind. Okay? So let's introduce variables. Let's introduce variables for each one. So P is the speed of the plane, and W, let's use that for the speed of the wind. Okay? So the other thing that we know about physics of this, physics of a plane moving with a constant speed, and that's the assumption that the plane has been moving with a constant speed is this, that the distance traveled is equal to speed times time. Okay? How long the plane has been going times its speed, which is what we're looking for, gives us the distance that it traveled. But in this case, the distance traveled is the same. Okay? It's 3,000 kilometers. But certainly, it didn't, the speed of the wind, the time it took for the plane to get to travel this was not the same, right? So let's see. This speed here is speed of the plane and the wind, because they're interacting. Speed here is the interaction between the plane and the wind. Okay? So, when the plane was traveling with a tailwind, that's when the wind speed and plane speed were working together, right? So, W for the tailwind, W plus P, that's when it took the plane 3 hours to get to the destination, times 3 hours equals 3,000 kilometers, right? That's with a tailwind. With a tailwind. With a headwind, the speeds of the wind and plane were working against each other. Okay, against each other. So if wind was blowing this way, the plane was going in the opposite direction. It doesn't matter which one you take the negative, but the point being that the speeds were not positive. They were not both negative or positive. They were working against each other. If this is positive, that must be negative. They're going in the opposite direction. And when the speed was interacting like this, it took the plane 4 hours to travel the same 3,000 kilometer distance. Okay? So when wind speed and plane speed are working together in the same direction, it takes the plane 3 hours to travel 3,000 kilometers. Speed times time is the distance traveled. When the speed of the plane and the wind are working against each other, in other words, they have opposite directions. If this is positive, that's negative. You could take the plane, the speed of the plane as positive and the speed of the wind negative. It makes no difference. But you must choose one of these to have an opposite algebraic sign than the other to indicate that the speeds of the wind and plane were working against each other. Why? Because this is the headwind. This is when the plane was traveling the same distance with a headwind. So these two variables must have opposite algebraic signs. Times 4, which is the time it took the plane to travel the 3,000 kilometers with a headwind. And now you have what? You have two systems, two linear equations with two unknowns, W and P. And we know how to solve this system, right? So, let me then, I'm quickly, as you can see, running out of space here. So, let me distribute the 3 into this. I'm going to move a little bit here. So 3W plus 3P equals 3,000. Then 4W minus 4p equals 3,000. Okay, so this is a system of two linear equations in two unknowns. So we want to get rid of one of these variables and solve for the other one, and substitute back and solve for the other speed. So because the plane variables already have opposite signs, so I'm going to multiply the top equation by 4 and the bottom equation by 3, so I get equal but opposite coefficients for the variable plane. Okay, so what do we get? Let's see that here. 4 times 3 is 12w. 4 times 3 is 12p equals 4 times 3,000, 12,000. Right? On the bottom, 3 times 4, 12w. 3 times minus 4p, that's minus 12p, equals 3 times 3,000, 9,000. Right? So let's come up here. We can now add these two equations here. But I'm going to add them here where I have space. So notice that the p terms or the plane terms drop out. They add up to 0, right? Because they have equal but opposite coefficients. And we intended the variable p to drop out so we can solve for the other variable. Okay, so what do we have? We have 12w plus 12w, that's 24w, equals 12,000 plus 9,000, we've got 21,000. Okay, we need to isolate w, right? So w is not isolated because it's got a 24 next to it. So divide both sides by 24 to isolate w. So we've got, so from this, we've got w equals 21,000 divided by 24, right? Let's see what that number is. We've got 875 miles per hour. Or, no, let's see. No, something is not right here. So something, this should actually be the wind speed or the speed of the plane, not the so 875. So let's see, 875, and then so 875. Then that means if we plug that in here, let's say in this equation, and then or kilometers per hour. Yeah, that's actually should be the speed of the plane, not the wind. And so let's see, maybe, so if this was P minus W, let's see, so P minus W, let's see. If we switch this, let me use this piece of scratch paper here, just to run. Oh, I see. Okay, so here's the thing. Let's switch these. So we have W plus plane times 3 equals 3,000. And this time, let's do the plane, because the plane is traveling the same distance. And this time, or in the same direction, but it's the wind that is opposite. So P minus W times 4 equals 3,000 kilometers. Okay, so let's solve this. I think that's the issue, because it's the wind that is changing direction, not the plane, or is assumed. But let's see if that is going to make the difference. So we have 3w plus, and this is, let's solve it with this, 3w plus 3p equals 3,000, and then 4p minus 4w equals 3,000. And then once again, if we eliminate the p terms, let's eliminate the p terms this time as well. So minus 3 and then 4 for the plane, and then we end up with 12w plus 12p equals 12,000, and minus 12p and minus 12p plus 12w equals minus 3,000. Yes, so this would make sense. So then the p terms drop out. We get 24w equals 9,000, and then 9,000 divided by 24 is 375 kilometers per hour. 375 kilometers per hour. And let's see. Okay, so it's still, we should have gotten the same answer, I would believe. So w times that, and we so 12,000, and then that. Yeah, so that's the issue. Let me revise this, guys, because the plane is going the same distance once with a tailwind and once with a headwind. So it's the plane that is changing, it is the wind that is changing direction. So this should be, it is the wind that is changing direction. So instead of w minus p, it should be minus w plus p. So the plane is going the same direction, the same distance, once with the wind cooperating, and the second time the wind is going against that direction. So I'm changing those two algebraic signs. Okay, and that, when we do that, the whole thing makes sense then. So then in here we will have minus 3. So here we would have the top equation is fine. Let's see. So let's see, 4 and then this. Okay, so then so in the top equation we have that. This is okay. The bottom equation, however, this would be minus 4w, and this would be plus 4p. So I'm adjusting these for the context of this problem, where the plane is assumed to have the same direction of speed or movement, whereas the wind is the element that is changing direction. Positive, meaning going in the same direction as the plane, or tailwind, and negative, meaning that it's going against the plane, like that. Okay, so then when we distribute the 4, and so if the if the wind has the minus 4 coefficient, then when we multiply the bottom and top equations by these numbers, it's the wind that is going to have opposite algebraic signs, right? 4 times 3w,
12W, 3 times minus 4, minus 12W. So it's the wind element that is going to have the opposite, but the plane piece will have, it will have equal, that one will have plus 12 like that. Okay, so that is plus 12p. Okay, so then this would be, so the wind drops out, the wind element drops out, 12W plus minus W, it drops out. Instead we get 12 plus 12, 24p is the variable that remains. And then p, or the speed of the plane, then is what we, which is what it should make sense then. 21,000. So 21,000 divided by 24, which is 875 kilometers per hour. So 875 kilometers per hour. So that's the speed of the plane. And then we can plug this back into any of the original equations and solve for the wind speeds. Let's say the first one. So using 3W plus 3P equals 3,000. Then let's substitute for P with 875. Like that. And then we have 3W plus 3 times 875. 3 times 875. We get 2,625 equals 3,000. And my apologies for cramming this answer into such a small space. I hope when I post this on Canvas, this whole solution for this worksheet, that things will make sense. But on the screen, I can only fit this much of it on the screen, like that. So that's the entire solution actually. So like that. Okay, and we're not done yet. So let me like that. Okay, so then we have 3W equals 3,000 minus 2,625. So that would be, let me calculate that, 3,000 minus 2,625 is 375, and then the wind speed is 375 divided by 3 divided by 3, which is 125. 125 kilometers per hour. So this is the wind speed, this is the plane speed. Okay, and that makes sense. So the adjustment that I had to make, or the assumption that I had to change, was that the plane was the element that was moving in the same direction. So I kept the algebraic sign the same, positive. It was the wind that was changing direction from tailwind to headwind the second time around when the plane was traveling the same distance. So I changed the wind coefficient to its opposite, and that fixed the answer to what makes sense. Okay. All right. I hope this helps understanding the solution to this problem. And I hope you, when you solve this problem on your own, you got the same answer like this. I hope our answers agree. Okay. So the next one, again, it's about two private planes that travel toward each other from cities that are 780 kilometers apart at speeds of 190 kilometers per hour and 200 kilometers per hour. Okay, and they left at the same time. In how many hours will they meet? Okay, so this is really worth noting, that the fact that the planes left the same time. And again, please pause the video if you haven't done this already and solve this problem, and then come back to it after you've had the chance to work out a solution on your own. Please do that before you see my solution here. Okay, I'm assuming you've done that, and now you're back. So when we read this problem carefully, this is one of those problems where drawing a picture really helps. So two planes are traveling toward each other, right? So let's call this plane 1 and this plane 2, right? They travel towards each other this way. One is going at 190 kilometers per hour. So let's say plane 1 is going at 190 kilometers per hour, and the other one is going in this direction at 200 kilometers per hour. Okay? At some point they meet, right? They ought to meet at some point. Let's say here, at this point. At this point, they're going to meet, right? Like that. So because this plane 2, is moving at a 10 kilometer per hour faster speed, then it will have traveled a longer distance than plane 1, right? When they meet, they must have traveled, this plane must have traveled a longer distance, a slightly longer distance than this plane, which is moving at a slower speed, right? So that's why this speed must be longer than that. That's one thing we should notice, okay? So we know that D1, let's say distance traveled by plane 2, or D2, and this is distance traveled by plane 1, D1. So we know that when they meet at this point, D2, that distance must be greater than D1, right? That's what we know. The other thing we should know is when they meet, because they left at the same time, that's why I highlighted that. They left at the same time. So when they meet, they must have been flying for the same duration because they left at the same time, right? So they must have been, at the time they reach each other, they must have been in the air the same length of time. Of course, D2, the plane 2 has traveled longer distance, but the time during which both planes have been in the air must have been the same. So we can say that T1, or the time that plane 1 must have been in flight, is equal to T2, which is the time the second plane must have been in flight. Okay? So then what they're asking is how many hours in how many hours will they meet? So they're really asking for this time. They're asking for T1 and T2. So T1 and T2 are really equal T, which is equal to number of hours after which the planes meet. Okay? All right, so if the time is the same, the time of flight for both planes is the same, then what can we say, what relationship does exist between the time, speed, and the distance traveled? Well, we can say that the whole distance is 780 kilometers, right? The whole thing is 780 kilometers. That's the distance between city 1 and city 2 and city 1. Okay, we know that. So D1 plus D2 is 780 kilometers, is what we're saying. Okay, so the time is what they're asking, how many hours they've been in flight before meeting each other in the air. So that would mean that, so this T for plane 1, so for plane 1, we have T equals the distance divided by speed. So D1 divided by 190 kilometers, right? Because time times speed equals distance. And let me write that here. Let me write that somewhere here. So somewhere, maybe here. So distance equals time times speed. Okay, we know that from basic physics. Okay, constant speed, that is. So then time is equal to distance divided by speed, which is what I've done. Time, because we're solving for time. So we need to find the time in relation to the distance and the speed. For plane 1, that's what it works out to be. Then for plane 2, and this is the same time, right? When they meet, we agreed, when they meet in the air, they must have been in flight at the same time. It's just that plane 2 has traveled a longer distance. But both planes must have been in the air the same duration. So T's are equal to each other, but the distances are not. So D2 divided by that speed. Okay? So these two times are equal, but they are the result of two different ratios, is what we're saying. Then, if these two times are equal to each other, then we can set them equal, right? Let's set these two, that one and that one, equal to each other. So these two ratios must be equal to each other because they're both equal to time, which is at the time these two planes meet is equal for both. So D1 over 190 D1 over 190 equals D2 over 200, right? That's D2. Okay, that D2. So we can say that about them. Now, what can we say about, we have an equation with two unknowns. We can't solve this. So we must find the relationship between these distances. The distance traveled by plane 1 and the distance traveled by plane 2, right? We know the total distance between two cities is 780 kilometers. So D2 then, D2, if we know either distance 1 or distance 2, we can solve for T, right? So if we know either D1 or D2, we can plug it into these equations and solve for T, and T is going to be the same. So it makes no difference which which D1 or D2 we know. Which one of these we know? We only need one of these. Okay? So, fortunately, we know the total distance between the cities, so we can write one distance in terms of the other. So we can say that D2, let's say, D2, that distance is equal to 780 minus D1, right? We can say D2 is equal to 780 kilometers minus D1, whatever D1 is. Okay, let's do that. So D1 over 190 equals D2 is 780 minus D1 over 200. So now we have a ratio in this equation, this ratio equal this ratio. Only D1 is missing, so we should be able to solve this. So let's solve it. And I'm running once again out of space, so I'll try to put the result here and finish it here. I'll try to do that. So for now, we have to clear the fractions. Let's cross multiply, because it's just one fraction equal another fraction. To get rid of this ratio fractions, we can cross multiply. So we can say that after cross multiplying, so after cross multiplying, we have this result. We have 200 times D1 equals 190 times 780 minus D1. Right? Cross multiplying. That's another way of getting rid of the fractions. So let me move up here and continue here, the solution. So 200 D1 is itself, 200 D1. On the other side, we have 190 times 780. Let's figure out what that is. So 190, we're distributing the 190 into these two terms. 190 times 780, we have 148,200. 148,200. 190 times minus D1 is minus 190 D1. Okay? So then if we move the negative 190 D1 to this side with the other D1, what do we get? We get 200 D1 plus 190 D1, right? Minus 190 D1 becomes positive 190 D1 when we move it to the left, right? It changes algebraic sign. Equals 148,200. This on the left, we have 390 D1 equals 148,200. So D1 is equal to 148,200 divided by 390. Divided by 390, we get 380 kilometers. So that means this D1, let me move this down. So D1 is 380 kilometers by the time these two planes meet. The plane 1 has traveled 380 kilometers. But is that what we want? No. We want how many hours the planes must have been in the air when they met. So all we have to do is plug that 380 into this equation to find time t. So t is equal to 380 for D1 divided by 190, right? Which is 2. So T equals 2 hours. T equals 2 hours. And that's the final answer there. But remember, the 2 hours is the same time that both planes must have been in the air. It's just the distance that they traveled is not the same because one plane is faster than the next. But they departed the cities at the same time. So when they meet, they must have been in the air at during the same period of time. Okay, I hope this matches what you have, and if not, I hope this answered any questions that you might have had. If not, let me know. Okay, so next we have the application. So all of these are applications of systems to solving problems, right? We deal with multiple variables, and for example, what technique did we use in this last problem to solve this plane problem? We used substitution, right? We found one variable in terms of the other, right? D2 was 780 minus D1. We substituted that for D2. We found what D1 was, and then we used the value of D1 to substitute back here and solve for time. So we use substitution. In the previous one, the previous example, this one, we used the method of elimination, right? We eliminated one variable, solved for the other one, and then after that we plugged back and solved for the other variable. So we've been using those techniques in real world situations, the method of elimination and substitution, that is. Okay, so here is another case, but this one is business oriented. It says suppose the total cost and revenue equations for a business are as follows, right? So they're given. Find the number of units X that must be produced and sold in order for the business to break even. So at break even, again, please solve this before you see my solution. So please pause the video and do that. So at break even, revenue equals cost at break even. Okay, and they want us to find X, or the units produced and sold at break even. Well, we can just set these two equations equal to each other because we know that's what happens at break even. Revenue equals cost. So revenue is 7x minus 600 equals the cost, which is 3x plus 400. Okay, so let's move. We're solving for x, so let's move all the x terms to one side and all the constants to the other. So 7x. Let's move the 3x to the left. When we do that, it changes from positive to negative. Let's move the negative 600 to the right. When we do that, it changes from negative to positive. So we end up with 4x equals 1,000, and x must be isolated, right? So we need to get rid of the 4, which means divide both sides by 4. X equals 250 units. So these many units must be sold in order for the business to break even. That means the business, after selling 250 units, the business is able to recuperate all of its cost. So what happens when the 251st unit is going to be sold? What happens when the 251st unit is sold? What happens? The company starts to make a profit. Because break-even, it means that it has recuperated all of its cost. Now, after that, any units of this product sold beyond 250 will bring in profit for the company. Okay? All right, I hope that matches your solution. And this one, again, please pause the video, solve this on your own, and then come back to the video for the rest of this. Okay? It says the supply and demand for an all-terrain skateboard are related to price by the following equations. Okay? Supply is that, the top equation, and demand is that. Where X is the number of skateboards produced and sold, and P of X is the price of each skateboard. So this is the price at supply, and this is the price at demand. Find the number of skateboards produced and sold to break even. Again, break even, at break even, the supply and demand are equal. The supply and demand equations are equal to each other. Okay? So in this case, we were given the price at supply, price at demand. But at break-even, supply and demand are equal, so we can set those two equations equal to each other and solve for X, which is the number of skateboards produced and sold to break even. Okay, so we can say 140 plus 4x equals 275 minus 5x, right? So we're solving for x. Let's isolate all the x terms and move the constants to the other side. So we have 4x minus 5x moved to the left becomes positive 5x equals 275. 140 moved to the right becomes minus 140. So we have 9x equals, adding these two, what do we get? Well, subtracting those, what do we get? We get 275 right? 275 minus 140, 135, right? 135, and then that divided by x. And what do we get? 135 divided by 9. Divided by 9, so we get 15. So after producing and selling 15 skateboards, then the company, All Terrain Skateboard, is gonna break even. So after that, the 16th skateboard is when they're going to make a little bit of a profit beyond the break-even point. Okay. All right. So I hope this was useful, this discussion, and I thank you for persisting through watching each video. All the credit goes to you for persisting through all of this material, and I thank you for that. And for now, have a nice day, and I'll see you again next time.